As mentioned earlier, a 12 gigahertz signal is applied to the copper feed wire. When the voltage is at the bottom of its sinusoidal, or trough, we have a concentration of electrons pushed to the end of the feed wire, thus creating a zone of negative charge, which corresponds to the maximum negative voltage. This concentration of electrons on the tip of the wire repels all electrons away, including the electrons on the top of the patch, and as a result, these electrons are pushed to the other side of the circular patch. Thus, one side of the patch becomes positively charged, while the other becomes negatively charged, thereby creating electric fields between the patch and feed wire, like so. However, when we reverse the voltage to the copper feed wire 42 picoseconds later, we have a concentration of positive charges, or a lack of electrons at the end of the wire, and thus the electrons in the patch flow to the other side. The voltage in the patch is flipped, and the direction of the electric fields are also flipped. Because the feed wire voltage oscillates back and forth 42 picoseconds between one peak and trough, the electric fields in the patch will also oscillate as the electrons, or current, flows back and forth. If we pause the oscillation, we can see some of these electric field vectors or arrows from the patch are vertical, and because they're equal and opposite, they cancel out. However, other electric fields are horizontal in the same plane of the patch and are called fringing fields. These fringing fields are in the same direction, and thus they add to each other, resulting in a combined electric field pointing in this direction. At the same time, electrons flowing from one side of the disk to the other, which is an electric current, generate a magnetic field with a strength and direction, or vector, perpendicular to the fringing electric field vector. As a result, we have an electric field pointing one way and a magnetic field pointing perpendicular to that. Let's move forward in time to where the voltage on the feed line becomes positive. And now we're at the peak of the sinusoid, 42 picoseconds later. The charge concentrations, or voltage, as well as the current, is all flipped, and thus the electric and magnetic fields point in the opposite directions. Electric and magnetic fields propagate in all directions, and by creating these oscillating fields, we've generated an electromagnetic wave, which travels in the direction perpendicular to both the electric and magnetic field vectors. Because the two sets of field vectors are not all in the same plane, but rather are curved, the propagating electromagnetic wave travels outwards in an expanding shell or balloon-like fashion, kind of like a light bulb on the ceiling. Let's simplify the visual so we can see the peak and trough, or top and bottom, of each wave, and note that the trough is just a vector pointed in the opposite direction. Additionally, the strengths of these field vectors directly relate back to the voltage and signal that we originally sent to the copper microstrip feed wire at the bottom of the stack. Which means, if we want to make these electric and magnetic fields stronger, we just have to increase the voltage sent to the feed line. It's like a dimmer on a light switch. More power equals a brighter light. Thus far, we've been talking about this aperture-coupled patch antenna as transmitting. However, it can also be used for receiving a signal. In this microchip, called a front-end module, we switch the antenna from transmit to receive and turn off the 12 gigahertz signal. When an electromagnetic wave from the satellite is directed towards Dishy, the electric fields from this incoming signal will influence the electrons in the copper patch, thus generating an oscillating flow of electrons. This received high-frequency signal is then coupled to the feed line where it's sent to the front-end module chip which amplifies the signal. Thus, these antennas can be used to both transmit and receive electromagnetic waves, but not at the same time. Two quick things to note. First, as seen earlier, this antenna has many more layers and is more complicated than we've discussed. For example, here are two circular patches. The bottom is used to transmit at 13 gigahertz, while the top to receive at 11.7 gigahertz. Additionally, there are two H slots and two feed wires to support circular polarization, a reflective plane in the back, and also there are multiple features for isolating the operation of one antenna from the adjacent antennas. We've included these and many more details in the creator's comments, which you can find in the English-Canadian subtitles. The second note is that there are electromagnetic waves of all different frequencies from thousands of different sources, passing through every point on Earth. Whether it be visible light from the sun, radio waves from radio or cell towers, or TV signals from satellites or towers. Therefore, in order to block out all other frequencies of electromagnetic waves, these antenna patches are designed with very exact dimensions so that they receive and transmit only a very narrow range of frequencies, and all the other frequencies outside this range are essentially ignored by the antenna. Let's move on and see how a single antenna can be combined with others in order to amplify the beam to reach outer space. This single antenna is only a centimeter or so in diameter, and using only it would be like turning on and off one light bulb and trying to see it from the International Space Station. What we need is a way to make the light a few thousand times brighter, and then focus all the electromagnetic waves into a single, powerful beam. Enter the massive Mr. McFlatface PCB, 55 centimeters wide, with a total of 1,280 identical antennas in a hexagonal array. The technique of combining all the antennas' power together is called beamforming. So, how does it work? Well, let's first see what happens when we have two simplified antennas spaced a short distance away. As mentioned before, one antenna generates an electromagnetic wave that propagates outwards in a balloon shape. At every single point in space, there's only one electric field vector with a strength and direction, and thus, the two antennas' oscillating electric field vectors combine together at all points in space. In some areas, the electric fields from the antennas are pointing in the same direction with overlapping peaks, and thus add together via constructive interference. And in other locations, they're opposite with one peak on one trough, and thus they cancel each other via destructive interference. We can now see that the zone where they add together constructively is far tighter or more focused than a single antenna alone. When we add even more antennas, the zone of constructive interference becomes even more focused in what is called a beam front. Thus, by adding 1,280 antennas together, we can form a beam with so much intensity and directionality that it can reach outer space.